Welcome to the deep dive. We take impactful research and, well, try to make sense of it for your world. Today, we're looking at something literally all around us: steel.
hmm Absolutely foundational.
Yeah, think about it for a second. Those huge skyscrapers, the car you drove today, maybe even the tools in your garage.
It's everywhere. Hard to imagine modern life without it.
Exactly, it underpins so much. But what makes it so useful? And maybe more interestingly, what's the big challenge when engineers work with it?
Well, that's the thing. For all its strengths, engineers have always wrestled with
Yeah.
this fundamental problem in material science, especially with metals like steel. It's what we call the strength-toughness trade-off.
Okay.
You want something incredibly strong, right?
Yeah.
Something that can take huge loads, resist bending. Think of a beam in a skyscraper holding up, tons of weight.
Makes sense.
But here's the catch. Traditionally, when you push that strength way up, make it ultra strong, you often lose its toughness. It becomes brittle.
Brittle like
Yeah.
like glass.
Exactly like glass. Think of really thick, strong glass. It holds a lot of pressure, sure, but drop it. Or if there's a tiny flaw and you hit it just right,
Shatters instantly.
precisely, it can't absorb that sudden shock. It can't stop a crack from just ripping through it.
So that's the paradox. How do you get both strong and tough? Toughness being that ability to, resist actually breaking even if a crack starts?
Yes, that's toughness. It's
Yes,
about
yeah.
resilience. It's the material's ability to absorb energy and stop a small flaw from becoming a catastrophic failure.
And getting both strength and toughness in steel, that's been the dream for decades.
Oh, absolutely. The holy grail of materials science, you could say.
Like wanting a bridge that's as stiff as rock, but also somehow flexible like rubber when things get really bad.
Yeah, sounds contradictory, doesn't it?
It really does.
And that apparent contradiction, it's limited so many designs for so long. The big question was always hanging there.
Yeah.
Can we actually get the best of both, or is this trade-off just baked into the physics of materials?
We'll get ready for a pretty amazing answer to that, because that exact problem is what we're diving into today. We're talking about a really groundbreaking discovery, a way to make steel both ultra strong and incredibly tough. It seems they've actually broken that old limitation.
It's really exciting stuff.
So our mission today is to unpack the science behind this. We're drawing from a paper published back in May 2020 in the journal Science, big deal journal.
Top tier.
The title is Making Ultra-Strong Steel Tough by Grain Boundary Delamination. We want to figure out what that actually means and, why it matters so much for, pretty much everything we build. Okay, so let's quickly nail down that difference again. Strength versus toughness is really key here. Strength, you said, is about resisting bending or changing shape, like that beam holding weight.
Exactly. It resists the start of deformation. How much load can it take before it permanently sags or changes shape? That's strength.
Got it. But toughness, that comes later.
Toughness comes into play once a crack is actually formed. A tiny defect, maybe an impact creates one. A material can be super strong, hold a massive load, but if it's not tough, bang, like that glass, it shatters.
Okay.
Toughness is all about absorbing energy when there's already a flaw and stopping that flaw, that crack, from spreading right through the material and causing it to fail completely.
So strong stops the crack starting, tough stops it finishing the job.
That's a good way to put it.
And with metals, pushing one usually hurts the other. Why? What's happening at the microscopic level?
Yeah, it really comes down to the metal's internal structure. Steel, like other metals, is made up of billions of tiny crystals. We call them grains.
Grains, okay, like tiny building blocks.
Sort of, yeah. Microscopic crystalline blocks, each lined up slightly differently. And where these blocks meet, those are the grain boundaries.
Right.
Now, traditionally, to make steel stronger, you'd make these grains really, really small. Or you'd add other elements, alloys that kind of lock everything in place, making it harder to deform.
And that works for strength.
It does. But the downside is that these superfine, strong structures often become really rigid. They can't easily absorb energy from an impact. If a tiny crack does form, it just zips straight through that stiff structure. There's nothing to slow it down or divert it, and that's brittleness.
The material is too unyielding, basically.
Exactly. Too stiff to handle a shock.
Which leads us perfectly to this new idea, this grain boundary delamination. Sounds complicated.
It sounds technical, but the idea behind it is actually quite elegant. This is how they've managed to bridge that gap.
So what does it mean, delamination?
Okay, so instead of that crack just ripping straight through the strong material, which causes it to fail brittly. They've engineered the grain boundaries themselves, those meeting points between the crystals, to actually separate or, as you said earlier, kind of unzip in a controlled way.
Unzip, so it's designed to come apart slightly.
In a very specific controlled manner, yes. Think
Yeah.
of it like, instead of a piece of wood splitting right down the middle, imagine a zipper coming undone along its seam. It releases the stress locally.
Mm.
This unzipping acts like a safety mechanism. When the material is stressed and a crack tries to form, instead of going straight through the strong grains, the crack's energy gets redirected.
Huh.
It gets channeled along these engineered boundaries.
Mm.
They absorb the energy, they blunt the crack tip, they make it incredibly hard for that crack to keep going straight.
So the steel is cracking, but in a way that's actually helpful. It's a controlled micro-failure to prevent a macro-failure.
That's a fantastic way to put it.
Yeah.
It yields just a tiny bit right at the crack tip along these boundaries. It dissipates the energy. This allows the bulk material to remain incredibly tough, able to absorb huge amounts of energy, even while the individual grains inside are still ultra strong.
Wow. Okay, so you're getting the strength from the grains themselves.
Right.
And the toughness from how these boundaries between them are designed to manage cracks.
Precisely. It's like building tiny shock absorbers right into the steel's microstructure. They've turned a traditional weak point, the boundary, into a source of resilience.
That's a complete rethink. Instead of just trying to stop any crack, full stop.
You're teaching the material how to handle a crack safely, how to fail gracefully at the micro level to prevent catastrophic failure overall.
That is genuinely ingenious, using the failure mechanism itself as a safety feature. And the paper's title really highlights how they do it, making ultra-strong steel tough by grain boundary delamination. The "by" is key. Now, the sources don't give us the exact secret sauce, the detailed recipe for how they make this happen chemically or physically.
No, that level of detail often isn't in the initial high-level publications, or it might be proprietary. But the concept points towards really advanced metallurgy. We're likely talking incredibly precise control over the alloying elements, the exact mix of iron, carbon, maybe manganese, vanadium, who knows what else, fine-tuning that recipe.
At a really fundamental level.
Possibly even near the atomic level.
Yeah.
And it almost certainly involves specific, maybe novel heat treatments. How you heat and cool the steel dramatically affects how those grains form and how the boundaries behave.
Or maybe even new manufacturing processes, like applying stress during formation.
Could be. Things like controlled rolling or forging techniques. It's about deliberately engineering that internal architecture, programming it, in a sense, to respond this way under stress. It's microscale intelligent design.
And we should definitely acknowledge the researchers. The paper lists L. Liu, Qinyu, Zhao, John L., M.X. Huang, and Robert O. Ritchie.
A significant contribution from that team.
And publishing in Science back in May 2020, that really signals the importance and the credibility. It's been rigorously checked by other experts.
Absolutely. It signifies a major leap, not just a minor tweak. A potential new paradigm for designing high-performance metals.
Okay, so we've got the cool science, ultra-strong and tough steel thanks to clever grain boundaries. But let's connect this back. What does it mean for us? For you listening, why should we care?
Well, stepping back to the big picture, having materials like this, it just opens up so many doors. It could fundamentally change how we build things, especially where safety and efficiency are paramount. Think about industries where you need extreme strength, but also total reliability, no room for brittle failure.
Like cars and planes.
Exactly. Take the automotive industry. Imagine car frames made from this steel. They could potentially be lighter, which helps with fuel efficiency or battery range,
Right.
but also intrinsically tougher. So in a crash, the structure could absorb more energy, deform in a more controlled way, potentially offering much better protection. It's a step change in crashworthiness, potentially.
And aerospace. Lighter planes are always the goal there.
Always. Lighter means less fuel burn, which is huge economically and environmentally, but you absolutely cannot compromise on safety. So if you can make components like the fuselage or wings from steel that's both ultra-strong and super tough, they could be lighter and more resistant to things like fatigue cracks or impacts from debris. That means safer flights, maybe less maintenance over the plane's lifetime.
Okay, that's significant. What about things that don't move? Buildings, bridges?
Oh, the potential in construction and infrastructure is enormous. Think about building in earthquake zones or areas prone to hurricanes or even designing structures to resist blasts.
You need materials that can take a hit.
Precisely. This kind of steel could lead to buildings and bridges that are inherently more resilient. They could absorb the energy from seismic waves or high winds much more effectively without collapsing.
So maybe taller buildings with less material? Or bridges with longer spans?
Potentially, yes. But crucially, structures that last longer need fewer costly repairs and provide much greater safety during extreme events. That has massive long-term economic and societal benefits.
It really paints a picture of a more resilient built environment. Does it trickle down further to manufacturing or other areas?
I think it does. In defense and manufacturing, you could see stronger, lighter armor, more durable components for heavy machinery that currently wear out or break. Think about industrial robots, components and turbines, maybe even things like advanced surgical tools that need to be incredibly strong, but absolutely must not snap.
Better performance, longer life, less waste.
Exactly. Improved durability often means using less material over the product's life cycle. So there are sustainability angles too. It could impact countless engineered products.
So it really feels like this isn't just some abstract lab result. It's got the potential to be a genuine game changer, redefining engineering, improving safety,
It really does. The potential is
yeah,
definitely there.
impacting things we use and rely on every single day, whether we realize the material science behind them or not.
Of course, there's always a journey from a lab breakthrough like this to widespread industrial use.
Sure, scaling it up, cost.
Exactly. Can the manufacturing processes be scaled up efficiently? Is it cost competitive with existing high-strength steels? How does it perform long-term in different environments, corrosion resistance, things like that?
More research needed there, obviously.
Absolutely. Those are the next steps for the engineers and material scientists working to bring this kind of technology into the real world.
Okay, so let's quickly recap our deep dive. We've looked at this really clever way scientists figured out how to beat that old problem, the trade-off between strength and toughness in steel. They did it by engineering the grain boundaries, the joins between the tiny crystals, to essentially unzip or delaminate in a controlled way.
Creating those internal shock absorbers.
Right, which deflects cracks, absorbs energy, and lets the steel be both incredibly strong and resistant to breaking.
It's a fundamentally new approach, designing resilience right into the material's microstructure, teaching it how to manage failure safely.
Which leaves us with a pretty interesting thought to chew on. How might this ability to actually engineer materials at this tiny microscopic level to teach them how to fail gracefully? How might that change the way we design and build basically everything around us in the coming decades?
It's a powerful question.
What other limits, other material paradoxes that we think are fundamental might we overcome with similar thinking? Think about that next time you look at a bridge or get in a car or even use your phone. The very stuff things are made of, it might be getting a whole lot smarter.